Okay, so good morning and welcome to the first session for this for this day. So the first speaker is Professor Mahua Datta. So she got her PhD from Indian Statistical Institute, Kolkata, and held visiting positions at ICTP, Italy. And now she is a full faculty member at ISI, and she works on geometry and topology. And she will speak on handle body decomposition of a manifold.
So thank you everybody. So I am going to give a talk on handle body decomposition of a manifold. I will describe what is a handle body decomposition, and then I will show how the handles originate, and finally I will discuss about Morse functions and how you can get handle body decomposition of a manifold. So what is a manifold? A manifold, you can consider it as a subspace of some high dimensional Euclidean space which is locally diffeomorphic to open subsets of Rn. For example, you can consider spheres of any dimension, torus, any surface of genus G, and cylinders. Now given any manifold or given two manifolds, for example, you would like to know whether they are diffeomorphic or not. So what are the tools that is available to us? So we have some algebraic invariants coming from the algebraic tools, homology and cohomology theories. However, it is not always an easy task to compute these invariants. So one way we can address this problem is by decomposing a manifold into simple objects in a very useful way so as to conclude something about the homology groups. So a handle of dimension n is a product of two balls. So it is, if I consider the Euclidean space Rk and I denote a ball in Rk by dk, then a handle is of index k is dk cross dn minus k. So a handle of index k and n minus k, they are actually the same object, but we will see in what way they will be different. So in dimension 2, if you look at, then any handle of index 0 or 2, that will be a disk. On the other hand, a handle of index 1, that is product of d1 cross d1, so it is a kind of a rectangle. Dimension 3, a handle of index 0 or 3, that is a 3 ball, and handle of index 1 or 2, that is a cylinder because it is a product of d1 and d2. Yeah, this is a closed ball. Yeah. Okay. So attaching of a handle. Suppose you have some manifold M0, which I denote by M0, an n-dimensional manifold which has some boundary, and dk cross dn minus k is the object that we considered just now. We have a smooth embedding phi from sk minus 1 cross dn minus k. Now this is a part of the boundary of dk cross dn minus k. What is the boundary of dk cross dn minus k? It is the boundary of dk cross dn minus k union dk cross the boundary of dn minus k. But I am considering only a part of the boundary, which is sk minus 1 cross dn minus k, and getting an embedding into M0. Then we consider the disjoint union of M0 and dk cross dn minus k. We define an equivalence relation on this. I identify the points x with phi x. So phi x, x is coming from sk minus 1 cross dn minus k, that means sphere cross a ball, and phi x is a point in M0. I am identifying them. The quotient space M1 is said to be obtained from M0 by attaching a handle of index k. Now you see the same thing, dk cross dn minus k, can be attached in another way. You can consider the other part of the boundary, for example dk cross Sn minus k, and get a smooth embedding psi from that into M0 and get the corresponding quotient space. You can get another quotient space. So if you attach along sk minus 1 cross dn minus k, then I will be saying that you have attached a handle of index k. On the other hand, if you are attaching along dk cross sn minus k, then that will be a handle of index n minus k. Okay, let us see what is. So I am describing here a handle attaching in dimension 2 and its also index is 2. So what is the handle of index 2? It is dk cross d0. So here it is d2 cross d0. What is the boundary? It is a handle of index 2. So I will be considering the boundary of d2, which is S1. So S1 cross D0, that means it is a copy of S1, a circle. So I must have an embedding phi from the circle into M0. M0, as shown in the figure, it also has a component S1 in the boundary. So maybe I take the identity map here. So once I consider the quotient space, it will look as shown in M1. So I am identifying a point on D2 cross D0 with the corresponding point in the circle, which is a part of the boundary of M0, and the quotient space is shown as M1. Here I am showing that M1 is a smooth, but in general it will not be a smooth manifold by this kind of attaching. So another example, so here we are considering a handle of index 1 in dimension 3. So handle is a D1 cross D2. Now its boundary will be D1, the boundary of D1 is S0. So 0 dimensional sphere, that means it has 2 points. So S0 cross D2, that means 2 copies of disks. So in the boundary, as you can see, there are 2 copies of disk. I have an embedding into M0, which will exactly fall onto the 2 disks which are being shown in the dark gray colors, and then the quotient manifold will look like exactly M1. Again, the point where we are attaching, we may not have the smoothness around that. For smooth attaching, what we have to do is actually around the 2 patches on the boundary, 2 disks, you have to get a small neighborhood around them, and similarly you have to embed that neighborhood inside M0. Then you can get a smooth resulting manifold M1. Okay. So this is what a smooth attaching, you can consider a closed neighborhood T of sk minus 1 cross dn minus k and an embedding psi from T to M0, such that psi maps this boundary of T minus this sk minus 1 cross 0, this is a bit technical, going inside the boundary of M0. Del T denotes the boundary of T and del M0 denotes the boundary of M0. Then if you look at the quotient space by identifying a points in del T with its image under psi, then what we get is a smooth manifold with possibly with boundary. The thing is to note is that the homotopy type of M1 will be different from that of the original manifold M0. Okay. The main result that we are going to address is a fundamental result in Morse theory, which says the following. If M is a compact manifold, actually you do not need compactness, so M is a compact manifold without boundary, then M can be developed from a ball Dn. So dimension of M is n. So I starting from a ball Dn and successively attaching to it some handles of dimension n, indices may be different. So successively attaching some handles, I can get back my M. So every manifold M starting from a ball, we can develop it to M by attaching certain number of handles. If M is compact, the number of such handles will be finite. Okay. So now I would like to say a few words about how the handles originate. It's a very nice connection between analysis and topology. So, we will describe what is a non-degenerate critical point. So, let us consider some smooth function f from M to R. M is a manifold and R is a real numbers. So, smooth real valued function on M. A point P on M is said to be a critical point of f if the derivative of f at P is 0. Now, M being a manifold, the definition of manifold says that it is locally diffeomorphic to Euclidean spaces. So, you can do all sorts of differential calculus on manifolds. As a result, you can define derivative of a smooth map as well. But even if you would not quite know of this, let us go to the situation where your manifold M itself is Rn. So, you have a smooth map f from Rn to R, and P is a critical point of f, means it is grad vector grad f, that is del f del x1 comma del f del xn at P, that is equal to 0. Okay. So, critical point P on M will be called non-degenerate critical point if its Hessian matrix at the point P is non-singular. The Hessian matrix for a function on Rn is simply consisting of del 2f del xi del xg. So, if this is non-singular at the point P, then I will say that P is a non-degenerate critical point of f. Now, the Hessian matrix is, this is a symmetric matrix. So, it will have all real eigenvalues. Now, the number of eigenvalues which are negative will be called the index of the critical point P. So, there will be, suppose n is the dimension, since it is non-singular, all the eigenvalues will be non-zero. Some of them is positive, some of them is negative. The number of negative eigenvalues will be called the index of the critical point. Yeah, everything. Yeah. So, some examples, it's a very simple examples in R3. So, I am just looking at only quadratic polynomials f, g and h. So, first case, the index is, see, in each of these case 0 0 0 is the only critical point, there is no other critical point, and the index, look at the Hessian of f, it will be the diagonal 2 2 2. In the case of g, it will be diagonal 2 2 minus 2, and in the case of h, it will be the diagonal 2 minus 2 minus 2. So, the index of f at the point 0 is 0, of g it is 1 and of h it is 2. Now, why we are just considering this very simple examples? Look at Morse lemma. Morse lemma says the following: if P is a non-degenerate critical point of f of index lambda, that means its Hessian has lambda many negative eigenvalues, then there exists a coordinate system x1, x2, xn around P such that f of x1, x2, xn equal to fp minus x1 square minus x2 square minus x lambda square plus x lambda plus 1 square dot dot dot, sorry, last term will be plus xn square. So, lambda many negative terms and n minus lambda many positive terms. So, if you are considering a function on Rn, then instead of saying that there exists a coordinate system, we would say that there is a coordinate transformation which will give you f in this form. So, that means it is enough to consider only the quadratic polynomials if you want to understand the local behavior of a function near a non-degenerate critical point, because finally any function looks like a quadratic polynomial. Okay. So, here I summarize the connection between critical point of index lambda say and to the level set. So I define for any function f on M, I define certain sets called MC, and C is a real number. This consists of all points x in M where the functional value is less than equal to C. Now suppose that P is the only non-degenerate critical point of F, and we choose two real numbers A and B, which are given here. A is strictly less than Fp and Fp is strictly less than B. See, Fp will be called the critical value of F, because P is a critical point, the value of the function at P will be called a critical value. So I choose a real number which is strictly less than this critical value, and one real number B which is strictly greater than this critical value. The results are the following. The topological type of MA is the same for all A strictly less than Fp. So as long as A is strictly less than Fp, the set of these sets MA consisting of all x in M where the functional value is less than equal to A will have the same topological type. On the other hand, so the topological type of MB is the same for all B strictly greater than Fp. So if you keep B strictly greater than Fp, then the level sets MB will again have the same topological type. But as you pass on from A to B, then there is a change in topology. The topological structure of MB is different from that of MA. So this will be explained in the next example. So we consider a very simple polynomial f on R2, which is y square minus z square. So as we have already observed that 0, 0 is the only critical point and the critical value is 0. So I choose a real number A which is strictly less than 0 and look at the corresponding level sets. We all are familiar with this kind of pictures. So the gray region, that is my MA, that means all points x where the functional value is less than equal to A, and all the colored portion, that is my MB where B is strictly positive. So I want to compare the topologies of MA with that of MB. Now look at the middle portion. There I have drawn some sky blue patch which I called capital H. So what is the topological type of that? This is simply, actually I am not talking about topological type, but just this is simply D1 cross D1. It looks like a rectangle. Topologically this is rectangle. Now if you look at this MA, which is the gray region, union the sky blue H region, that has the same topological type as capital MB, which is the whole of this colored region. You can squeeze through this dark blue region to fall it on MA union MH. So MB has the same topological type as MA union H. Now so you can see some change in topology, because MA to start with was a disconnected thing, and if you are looking at MA union MH, that is a connected object. So certainly the topology has changed. Now observe this, that the critical point that I was considering, this is 0, 0, the index was 1, because there is exactly one negative term in the quadratic polynomial. So index was 1, and I have attached H to MA. H is D1 cross D1 and it is attached along S0 cross D1. So two copies which are showing the attached. So this is a handle of index 1 is attached. So what I want to point out, the correspondence, that you have a critical point of index 1 and you are attaching a handle of index 1. So now I consider this polynomial. The whole figure you can get just by So look at the previous figure, there is no difference actually. I have taken a solid of revolution by taking revolution about the z axis. So I go into the 3 dimension. Again your handle here will be now, because it is a revolution around z, so the handle is d2 cross d1, which is attached along 2 copies of d2. Instead of d1, 2 copies of d1, now I have 2 copies of d2, which of course I cannot show you in the picture. So again MB is connected, MA was disconnected, and index of the critical point is the index of the handle H. Sorry. Okay. So we can summarize these observations into theorems. First, let us define the subsets. For any 2 real numbers a, b, b greater than a, we can define sets of the form M superscript ab as follows, which consists of all points x in M where the functional values lies between a and b. The theorems are the following: if MAB is compact and contains no critical point of f, then MA is diffeomorphic to MB. For example, if you go back to this picture, as I said that if you had taken, if you change the value of A and look at these gray regions, it will only come closer or go away from the 2 diagonal lines that I have drawn, but the topological type will not change. So this is summarized in this theorem, that MAB is compact and contains no critical point of f, then MA is diffeomorphic to MB. But if it contains exactly one non-degenerate critical point, then MB can be obtained from MA by attaching a handle of index k and a collar. Okay, what do I mean by collar? So look at this picture, H is the handle and the blue, deep blue part, that you can consider as a collar. Why it is attached? To make the thing smooth, because as I was attaching the handle in the middle, the boundary was not becoming smooth. There are 4 corners that you can see at the join of H and MA. So to make it smooth, I have to attach a collar. Then the diffeomorphism type of MB will be same as that of the manifold. Okay. So the main point to note is that if you have a critical point of index lambda, then to get MB from MA, you have to attach a handle of index lambda. Okay. So this was only the local picture, and now I want to give an example in so it's a global example. So I consider a torus, vertical torus. You can see that example in the book of Milner on Morse theory. It's a very famous book. So you have a torus. Torus is actually obtained from, it's a tire, basically it's a tire. So I put it in a vertical way. So its section is each section is a circle. So the sections are shown here. Now I am considering a function h, very simple function, which is taking a point. So this is embedded in R3. So a point is denoted by x, y, z. So h of x, y, z, that will be equal to z. That means it is the height of the point from the level shown below. Okay. So just looking at the picture, we can say that it has exactly 4 critical points. Okay. So critical points are shown by P, Q, R and S. Okay. Why P is a critical point? Because it is the absolute minimum for the function h. The height is the lowest here. As you go up, the height function increases, and as you reach S, that is the maximum value of the height function on the torus, because there is no other point beyond this. So P being a minimum and S being the maximum, so they are certainly critical points of the function h. What about this q and r? So, from q I have shown two directions, one is v and another is w. V is in the plane of the screen and w is coming out. So, if you move along the curves in the direction of v or in the opposite direction of v, then the curves are going up. See, I have shown 4 curves going out of q. 2 of them are going up, which are in the direction of v or minus v, and 2 others in the direction of w and minus w, they are going down. So, if you are evaluating your function h on the curves in one direction, the height function is increasing. In case of the small circle, the height functions are decreasing. So, if you restrict your function h to the plane of the paper only, then q becomes a point of minima. On the other hand, if you are considering a plane which is perpendicular to the plane of the screen, then you are getting the small circle as section, and then the h function restricted to that will have a maxima at q. So, these are saddle points. In certain directions the function is increasing and in certain direction the function is decreasing. So, I am summarizing it here. So, the critical points are p, q, r, s. Okay, sorry. And so, you have 2 saddle points, that means the index must be equal to 1. At p, it is the minimum. So, if it is a minimum, then the index is so if something is a minimum, the index there will be 0. Why? Okay, let us go back to this expression here. Okay, look at Morse lemma. It says locally the function will look like this. So, if something if p is a minima, then there cannot be any negative squares. Okay? Every term has to be positive because the point p is a minimum. So, whichever direction you move, the function has to increase. So, all the terms must be positive. So, the index has to be 0. On the other hand, if p is a maximum point, whichever direction you move, the function has to go down. So, all the terms has to be negative and the index will be maximum. So, at p and p the index is 0 and at s the index is 2. On the other hand, at q and r the indices are 1. Okay. So, we look at this picture now, and so we have studied the critical points. Now, I want to look at the level sets. So, if your functional value lies between a and b, what are a and b? A is the functional value at p, b is equal to hq. So, as long as your height function takes the value z between a and b, the level set, which is shown in gray, looks like a disk. So, you have a torus and you have cut off some portion, that will be like a disk. On the other hand, if you are your z, the functional value is between b and c, so this is a cylinder. And thirdly, when your functional value is between c and d, then it is just you take out one small disk from the cylinder, from the torus. So, these 3 types have different topological types. Now, as I have passed through Q, I have a critical point of index 1. When I go from the second picture to the third picture, I have passed through a critical point which is of index 1 again. And finally, when I have covered everything, we have a critical point of index 2 at S. So, I would like to explain this change in the next figure. So, whenever the functional value is between A and B, the level set, that means all points where the functional value is between A and B, is a disk. And when the functional value is between when the level set, see, I have denoted the level set here by mz, and z I have taken between C and D. Okay. Here it is between B and C, so I have a cylinder. I want to say that you can get a cylinder out of a disk by attaching a handle of index 1. So, this deep blue thing is a handle of index 1 which is attached. So, handle of index 1 means this is D1 cross D1, you have attached it along 2 copies of D1. Now, it is not very simple to see that, okay, but if you are good in understanding this topological thing, then it is easy. But I would like to say that they have the same homotopy type, the cylinder and the disk attached with one handle. They have the same homotopy type. So, look at the boundary part. Here, in the case of a disk attached with a handle, it has 2 parts in the boundary, each of them is homeomorphic to a circle, and the same is true for the cylinder as well. You have 2 components in the boundary, each of which is homeomorphic to a circle. In fact, if you attach a see this, we have only attached a handle. If we attach a collar around that, then it will be exactly diffeomorphic to the cylinder. So, as we pass through a critical point of index 1, I have attached a handle of index 1. So, from cylinder to this figure, third figure, I have attached again, because the point R was also a critical point of index 1. So, I have attached a handle of index 1 and got this third figure here. And finally, I have attached a handle of index 2 in dimension 2 to get the whole torus. So, this is just an example, but this is exactly what happens if you work with a function which has all critical points non-degenerate. So, a smooth function f from M to R is said to be a Morse function if all its critical points are non-degenerate. Now, the question is, does such function exist or not? It says that every smooth manifold admits a Morse function, and not only that, there are many Morse function on this. Given any smooth function, you can perturb it a little to get a Morse function. So, this is the main theorem. So, if f is a Morse function on a manifold M with critical points P1, P2, ... Pk, so there may be countably many. See, one point I forgot to mention, that critical points of Morse functions are isolated. So, the Pi that has index lambda I, then M has a handle body decomposition which admits a handle of index lambda I for each I. So, what we have just observed for a torus, that is true in general. So, I have given a proof here. So, you take a Morse function, look at all its critical values C1, and we arrange them in an increasing fashion. I choose real numbers AI which lies between 2 consecutive critical values, and look at sets M superset AI plus 1 which is obtained from, yes, yeah, but the proof also works for infinite case also, open manifold case also, there you may be yeah, compact case you can only have finitely many points. Yeah. So, in fact, the first statement that I wrote that was only for compact. So, when you are having compact thing, you have only finitely many critical points. So, you will be attaching only finitely many handles. So, I am looking at successively these sets MAI and MAI plus 1, they differ by sets MAI, AI plus 1. Now this M AI plus 1, that corresponds to attaching a handle of index lambda I plus 1 corresponding to the critical point Ci plus 1. That is how I can develop this M out of a ball of dimension n by attaching successively some handles. Now what is the outcome of this? How we can use this information? In fact, it's an immediate corollary to the above, that every smooth manifold has the homotopy type of a CW complex. So what is a CW complex? CW complex consists of certain cells of some dimension. Cells means they are just homeomorphic copies of balls. They may be lower dimensional thing. Now in this figure which I have shown before also, I have put a black line in the middle. That is simply stands for your dn minus k. Sorry, yeah, this was my d1. Yeah, this is dk, stands for dk. I have squeezed this h portion. So if you look at the h, in middle you have a deep line, black line. You can squeeze this h portion fall onto this line segment. So basically we will be left with 1 dk. So handle was dk cross dn minus k. I was attaching it around the boundary, and you are left with this. So finally what I want to say is that you can get this way a CW structure for a CW manifold M, and once you have a CW structure, you have some nice observation. Okay, I am just recalling here a few facts from algebraic topology. So given any topological space, you can associate to it certain groups which we call homology groups. For each integer q, you have HQMZ, it's a homology group. If M and N are homotopically equivalent, then HQMZ is isomorphic to HQNZ. Further, if M naught is contained in M1, then we can talk about relative homology groups HQ M1 M0, which are isomorphic to HQ of the quotient space M1 quotient M0 for q greater than 0. Then I define certain numbers, integers. So beta qm, these are called the Betti numbers of M. These are ranks of the homology groups. These are certain invariants for the manifold. So if two manifolds M and N are homotopically equivalent, then their Betti numbers will be the same. Another invariant is the Euler characteristic of M, which is called the chi-M, which is the alternating sum of these Betti numbers. So these are some important algebraic invariants which we study to study the manifold also. So this is the Morse inequalities which were proved by Morse. So it says that if f from M to R be a Morse function on a compact manifold M, and let Ck denote the number of critical points of f of index k, then we have the following relations. It says that the kth Betti number, that is the rank of the kth homology group, that must be less than equal to the number of critical points of index k, Ck, and chi-M, that is the Euler characteristic of M, that will be the alternating sum of the number of critical points of index k. So you can compute the Euler characteristic starting from a Morse function, and Morse functions are abundantly many on any manifold. So it is possible that you come across one of the Morse functions and then look at its critical points. If M is compact, then the number of critical points will be finite. It may not be very difficult, and then you can easily compute the Euler characteristic. It is only dependent on the number of critical points of index k. So that is how you have some hold on the invariants of the manifold. So I'll just try to give a proof, discuss a proof of this. Now what happens when you are attaching a handle of index k? So you are attaching a handle of index k along the boundary, so Sk minus 1 got collapsed. So relative homology of M1, M0. So you are quotienting out M0. So when you are quotienting out M0, you are actually quotienting out Sk minus 1 on dk, because your handle was dk cross dn minus k, and you are attaching along the boundary, that means Sk minus 1 cross dn minus k. So Sk minus 1 has already been embedded in M0. So when you are collapsing M0, those copies of Sk minus 1 is getting collapsed. So basically you are left with HQ M1 M0 is equal to HQ dk Sk minus 1. And we all know, means it is very well known that these are, so when Q is equal to K, then this is isomorphic to Z, otherwise this is 0. So basically when you are attaching, okay, let us go to this. So again the proof is almost similar. You arrange your critical values, take some real numbers ai between two successive critical values and construct corresponding level sets, and write down dn equal to m0, which is contained in m1, contained in m2, and finally you get your m, where mi plus 1 is obtained from mi by attaching a finitely many cells. See, as you are passing through the point, say any critical value ci, it is not necessary that there will be only finitely many, only one critical point. There may be finitely many critical points, but the corresponding to each critical point you can attach a handle, and the handles can be attached disjointly. So here mi plus 1 is obtained from mi by attaching a finitely many cells. So this is also one known fact, that if you look at the homology functor HQ, this is subadditive. That means rank of HQ mz, that will be less than equal to summation rank of HQ mi plus 1 mi. Now HQ mi plus mi, that I have already calculated here. If you have attached a handle of index k, then HQ m1 m0 will be non-zero provided q is equal to k. So only if from going to mi plus 1 you have come across a critical point of index q, HQ mi plus 1 mi will give you something non-zero, otherwise it will give you 0. So what happens, the left hand side, the rank of HQ mz, this is actually your beta q, there is a qth Betti number, and the right side only non-zero terms will appear if you have come across a critical point of index q, that will contribute to 1. So finally this is equal to the number of critical points of index q. So these proofs are not very difficult if you know the language of homology and some properties. So so that was our main goal. Starting from aim, we wanted to compute its invariance. We could not, so we have computed at least one invariant using the Morse function and looking at its critical points. That is the Euler characteristic, and we have got some bound on the Betti numbers. So this is what is important from our point of view. Okay, I would like to end my talk. The most of the thing, it has been taken from this book, is by John Milner. It's a wonderful book on Morse theory, and everyone interested in differential topology must have seen this book. So this is all. Thank you.
So I'd like to start by thanking the organizers for inviting me here. To add to Jaya's introduction, I'm actually a physicist who's interested in the interface area between mathematics and physics. So I'd especially like to thank the organizers for actually inviting someone with that research interest to this conference. So the first speaker of this conference said at some point that physics and mathematics are close friends. I rather like that, and most of my talk is going to be about a point of intersection between geometry and physics. And geometry and physics have had several points of intersection, and the oldest is actually something which has to do with Einstein's theory of gravity. So most of you have probably just heard about it. So Einstein used Riemann's description of curved shapes in geometry as the language for his theory of gravity. And the details of this geometric language is really very important for applications. In fact, if you want to precisely measure the path of light rays near the sun, or if you want to calculate the precise trajectory of planetary orbits, Kepler's laws are not enough. You need to actually use this geometric language. And even the GPS system which tracks down objects on the Earth uses this geometric language. So there are many such examples of points of intersection between geometry and physics. So something that interests me is a new point of intersection that has come up in the last 10 years, maybe the last 7 or 8 years, which is Ricci flow. So a lot of this talk is going to be an overview of Ricci flow and how it comes about in physics. So what is Ricci flow? Why is it of interest in math, and how it comes about in physics? And I prepared the talk keeping in mind that there are several undergrad students also in the audience. The organizers wanted something like that, so I apologize in advance to all the experts. So what is Ricci flow? Well, in a line, Ricci flow is like a flow through geometries, and it's of great interest in mathematics now because it was used to prove the Thurston geometrization and the Poincaré conjectures, and many new tools and techniques were introduced in the process. So this field is really very alive. And this flow also comes very naturally in physics as a class of flows called renormalization group flows. So I'm going to try to give you a rough idea of what these renormalization group flows are as well in this talk. Okay, so Ricci flow has been used in mathematics recently to prove these conjectures. It also arises naturally in physics. This is the point of intersection between the two areas. What are the implications of this point of intersection? So before we answer that, just some basics. So I told you that Ricci flow is a flow through geometries. What is Ricci flow defined on? It's defined on a smooth manifold with a Riemannian metric G. Now I wanted to give you a rough idea of what a smooth manifold is. The last speaker made it a little easier for me because she already introduced a lot of the terms that I was trying to describe. But because there are undergrad students, I just want to give you a rough idea. This is not a rigorous definition. There's no time for that, but here's a rough idea of what a smooth manifold is in 2 dimensions. So a smooth manifold is a description of a curved space. So in 2 dimensions, it's a nice intrinsic definition of a curved surface. So suppose I was not a mathematician, okay, and I wanted to construct a curved surface. So I have bits of paper, I have glue, I have scissors. So how would I do that? I would take my paper, I would cut out shapes out of the paper, I would glue them together, and if I want a smooth surface, I would glue them together carefully so that my result is a smooth surface. So this is roughly the idea. So what a smooth manifold is it is a topological space M with some additional properties which I'm not going to describe here, such that you break up this topological space into subsets UI. So you can find subsets UI such that there are homeomorphisms from UI to open disks in the plane. Okay, so I'm describing a 2-dimensional smooth manifold. And these phi i's, these maps, are homeomorphisms. So this makes M a topological manifold, but then I require additional conditions from those maps phi I. These additional conditions will ensure that M is a smooth manifold. So this additional condition is the analog of what I said. Take cutouts of the plane and glue them together carefully so that the result is smooth. So M looks locally, M is locally diffeomorphic to the plane. And similarly, an n-dimensional smooth manifold is defined in an analogous way. It looks locally like Rn. Okay, so I gave you a rough idea of what is a smooth manifold. Now I want to give you a rough idea of what's a Riemannian metric on a manifold. This is a very rough, non-rigorous idea of what it is. So what I'm going to describe now is not really the Riemannian metric, but is something that is a consequence of having a Riemannian metric. So to give you an idea of what it is, just look at the plane. Okay, if I take the Euclidean plane, it comes with this notion of Euclidean distance. Okay, so if I label my plane by coordinates x, y, my infinitesimal distance between 2 points is ds, and ds square is dx square plus dy square, which I can write in this form, where I have here, okay, I have here a column vector dx whose entries are dx and dy, and I have this matrix G, which is just the identity matrix, and this is the transpose of dx. Okay. So I call G my Euclidean metric, and I can use this notion of distance to define areas, for example. Okay. So one natural question that you can ask is, can you define other distance functions on the plane or the subsets of the plane? So the answer is yes. So for example, let me take the open unit disk that I have drawn out here on the plane. Okay, this is my open unit disk. Of course, I know that I can put the Euclidean distance function on it, but I'm going to give you a picture of another distance function that I can put on this open disk. So this is my open disk again. Okay, I now have another distance function which you will see out here. So if I just had this was my Euclidean distance, but then I have this additional factor out here. Okay, and so this G is now G Euclidean divided by this object. So using this new distance function, this is called the hyperbolic metric on the unit disk. Using this distance function, I now have a formula for my area. Okay. If I use this formula for my area, then all these triangles, okay, I say triangles within quotes because they don't really look like triangles, all these triangles have the same area with respect to this distance function. Okay. Now this doesn't look really like a triangle. For example, this line looks curved if you think about it using Euclidean distance, but it is the path of shortest distance between 2 points using this distance function. Okay. So this metric is called the hyperbolic metric. Okay, so what we call metric was really related to the distance function, but it turns out that it's also related to the intrinsic curvature of a manifold. Okay, so again, intrinsic curvature has got a very precise definition, no time to go into that. So I'll just try to give you a rough idea of what it is. So there are many manifestations of intrinsic curvature. So for example, if you say that straight lines are paths of shortest distance on a curved space or on a manifold, then on a sphere, if all these paths of shortest distance are arcs of great circles. Now if you take two nearby such straight lines, which are these two arcs of great circles, these lines, even though they are initially parallel, will not remain parallel. They will converge on the sphere. On some other kinds of curved spaces, they may diverge. So this convergence or divergence is actually proportional to the curvature. So if the two straight lines converge, then that's a manifestation of positive curvature, and if they diverge, it's a manifestation of negative curvature. Similarly, on the sphere, I can define a triangle which is made up of three straight lines within quotes on the sphere, which are arcs of these great circles. Now if you add all the angles of this spherical triangle, then the sum of those angles is not pi. It's actually bigger than pi. This is again a manifestation of positive curvature. I'll go back to my previous slide. Here are again triangles on this space with this different distance function. And on this, if you take these triangles and you add up the sum of the angles, this will be actually less than pi. This is a manifestation of negative curvature. So the message from this slide is that you had this thing which I call the manifestation of curvature, which is that the sum of the angles of the triangle is not pi, and that came about in this space because of having this metric which is not Euclidean. So there is an intimate connection between metric and curvature. Okay, another manifestation of curvature on a sphere, take a circle. Okay, the radius of the circle as measured on the sphere is that. So take the ratio of the circumference to the radius, it will not be 2 pi on the sphere. So as I said before, non-Euclidean metrics are actually natural on curved spaces. So there is this connection between metric and curvature. So for example, take the two-sphere, unit two-sphere, which is a subset of R3. Okay. Now given the Euclidean distance on R3, I can actually find a natural distance, infinitesimal distance between 2 points on the sphere, which looks like this. I've used the natural coordinates theta and phi by which you would label points on the sphere. And again, I can write the square of this distance as I wrote before, which is in terms of this vector dx and this matrix G. Okay. Now you see that this matrix has entries which are some real valued functions. So here's my rough idea of what is a Riemannian metric. On any n manifold, smooth manifold, if you have a distance function, then you can write that infinitesimal distance in this way in terms of this matrix G, whose components are real valued functions, the matrix is symmetric, and all its eigenvalues are positive. Okay. So this is not a Riemannian metric. Actually, this is a consequence of the Riemannian metric, but I think this is the easiest way for us to get to the rest of my talk. So for the purposes of this talk, I will take this matrix G to be the Riemannian metric. Okay, so the natural question that you can ask at this point of time is, we saw that, for example, on the unit open disk, I could either put the Euclidean metric or I could put the hyperbolic metric. So can you put any arbitrary Riemannian metric on a manifold M? The answer is no. But there is a very nice theorem, a classical theorem called the uniformization theorem, which holds for surfaces. So let me state the theorem first. So the theorem says that every compact connected orientable surface admits one of three special metrics. And more precisely, suppose my compact connected orientable surface has no holes, okay, then it always admits a sphere metric which has constant positive curvature. And if my surface has one hole, this is what we call the torus, then it always admits the flat metric whose curvature is 0. And if it has more than one hole, it admits a hyperbolic curvature, metric whose curvature is constant and negative. So there are three special metrics in 2 dimensions. Okay, so what about 3 dimensions? Okay, are there any special metrics in 3 dimensions? Well, you can't really produce a very, very simple statement which is the analog of the uniformization theorem, because there are, if you start doing that, if you start with some special metrics and look at general 3 manifolds, then you will find that it's not easy to formulate such a statement. But Thurston had a more complicated conjecture which concerns 8 special metrics in 3 dimensions. So I'll try to give you an idea of Thurston's conjecture, and the reason I'm going to do that is because Ricci flows very important in mathematics because it was used to prove that conjecture. Okay, so what is Thurston's geometrization conjecture? So you start with any compact connected orientable 3 manifold, and you have to first do a canonical decomposition of this 3 manifold, which is done in 2 steps. Okay. So in this way, when you remove all the essential 3 spheres out, you can actually decompose this manifold into these pieces in a unique way. These pieces are called prime manifolds. This is called prime decomposition. So this is the first step. So Thurston's conjecture says, first do this to a compact connected orientable 3 manifold. Then the next step is something called a torus decomposition. Now in each of these prime manifolds, if they exist, remove essential tori. So for example, take this kind of a prime manifold. An essential torus is a torus or a cycle tire which has not been filled in, so it's hollow. Okay. So you take an essential torus, you remove all the essential tori out of this prime manifold. Okay. So you will be left with pieces which have toral boundary, which are compact with toral boundary, and this is called the torus decomposition. Yeah. Yeah. You know something about the prime manifolds. For example, you know that there are prime manifolds. Okay, suppose you start with a simply connected 3 manifold, then you know what the prime manifolds will be like. They will not have these essential tori. Okay. When it has no more essential spheres. They will either have these essential tori, or they will be they will be simply connected, or they will be of the type S2 times S1. Yeah. Okay, so in each prime manifold, if the prime manifold has some essential tori, okay, remove them. Okay. This is the second decomposition. This is called the torus decomposition. Now, Thurston's conjecture says first do these 2 decompositions, and then you'll be left with all these resulting pieces. These resulting manifolds, after this decomposition, admit one of 8 special metrics. Well, those 8 special metrics are like in your 2-dimensional case, they are analogous to that, which is a 3-sphere metric, hyperbolic metric, R3, and then bundles over S2, H2, and R2. Okay. So the Poincaré conjecture, which is actually much older and it's a 100-year-old problem, this follows as a special case of the Thurston conjecture, but I don't have the time, so I'm going to skip all those things because I want to get to Ricci flow. So I don't have the time to explain the connection between the 2. Okay, so I want to give you a rough idea now of how the Thurston conjecture was proved. So it was proved very recently by Perelman in 2003, but the idea dates back to other mathematicians like Hamilton from 1982. Idea looks really simple, almost naive. Okay? So the idea is to start with a partial differential equation on this smooth manifold with the Riemannian metric. And what does the partial differential equation look like? Well, it's, okay, I have to explain my notation here. I told you that the Riemannian metric was a matrix for the purpose of my talk. It was a symmetric matrix with functions as real valued functions as entries, and it had all positive eigenvalues. Okay, so Gij now is the ijth component of that matrix. So I'm writing this whole equation in component form. So dGij by dt is minus some constant times this object Rij called the Ricci tensor. Okay. This object on the right hand side is a measure of the curvature of the smooth manifold. So I already told you a little bit about curvature. So this is actually a measure of the curvature. Now this partial differential equation is nonlinear, but let me give you an idea of what the right hand side looks like. So the right hand side looks like something which has no more than 2 derivatives of Gij with respect to the coordinates. Okay, so there's lots of other terms there and it's nonlinear, but this is the rough idea of what it looks like. So the curvature depends on the metric. Now this is actually a parabolic PDE. It's like a heat equation. Okay, and this equation describes a flow of geometry or a flow of curvature. So how was this equation actually used to prove Thurston's conjecture? Okay, so to see this, let's just consider that partial differential equation on a compact connected orientable surface. Okay. So the idea is, this is my partial differential equation. Okay. So I start with one initial condition, okay, and then I flow. So that initial condition could be any Riemannian metric on that manifold. And then let's see what it flows to. Now the result is in 2 dimensions really nice. If my surface has no holes, then whatever be the initial condition on the surface, whatever be that Riemannian metric, this flow smooths it out. Okay? Smooths it out so that it finally flows to the round sphere metric. And then of course this flow leads to a singularity in the sense that the round sphere shrinks to a point, but that's not a problem because we already know that this surface with no holes admits the round sphere metric. Okay. So similarly, if it has a hole, you can show that it flows to the torus, to the flat metric, and if it has more than one hole, it flows to the hyperbolic metric. So in the previous slide, I told you that this Ricci flow was like a heat equation, was like a nonlinear version of the heat equation in the sense that you have one derivative with respect to t out here, 2 derivatives with respect to the space coordinates x. Of course, you have many other terms. But this behavior of the Ricci flow is very reminiscent of a heat equation. So what does a heat equation do? Well, a heat equation is an equation for the flow of temperature on a space. So if you have an initial concentration of temperature, the heat equation slowly smooths it out so that the temperature becomes equal everywhere. Well, similarly, the Ricci flow seems to smooth out curvature and lead you to a constant curvature metric. Okay. So now we see that Ricci flow can actually prove the two-dimensional uniformization theorem. You can ask in 3 dimensions if Ricci flow can actually prove Thurston's conjecture. But the one important point is, can Ricci flow actually, within quotes I say, implement the canonical decomposition? Okay, so because Thurston's conjecture is more complex, it says first you do a canonical decomposition of the manifold and then the resulting pieces admit one of those 8 special metrics. So the Ricci flow has to actually also somehow implement this canonical decomposition. And the real reason why Ricci flow is able to do that is because it's nonlinear and it can lead to singularities. So let me give you an idea of what that happens. So this is a very complicated subject. I'm not an expert on that. I've only read one portion, one of Perelman's papers, but for completeness, I just want to give you an idea of this. So here's my 3-manifold with, again, I do the same thing. I take this compact connected orientable 3-manifold. I put some arbitrary Riemannian metric on that as an initial condition, and I start my Ricci flow. Now, generically, the Ricci flow leads to singularities. Because it's nonlinear, it's a 3-dimensional case where the singularity is actually quite complicated. But one of the possible singularities looks like this. There is a pinching of the manifold. This is called a neck pinch. And one of Perelman's successes was actually identifying the exact geometry of this neck pinch. So the neck pinch is actually S2 times an interval. So this proving that this is an S2 times an interval was one of his key achievements. So the moment you have a neck pinch and the moment your curvature becomes larger than some bound that you have set, then what you have to do is you have to do surgery. You have to remove this neck pinch, okay, and then you have to fill it up with 3 balls, and then you have to start your Ricci flow again. This is another technical point. You need to exactly know the geometry of this neck pinch, okay, so that you know what is the initial condition on the Ricci, on the surgered pieces. Now, if you do this Ricci flow, then the pieces may already admit one of those Thurston metrics. But if they don't, then your flow will continue, and then your flow actually leads you to something which looks like this. This is called a thick-thin decomposition, where there are regions of very large volume, and there are these thin regions. Now it is known exactly, so one of the other achievements is to identify exactly that this is what the thin pieces look like and what the thick pieces look like. Then you can do surgery and remove the thin pieces out, and then thin pieces are already known to admit one of those special metrics, and the other pieces you again continue Ricci flow and you find that they admit one of the Thurston metrics. Okay. Yeah. Yeah. So that is one of the theorems of the torus decomposition, which is that you can always break the manifold into this. You can always take out these find disjoint essential tori and remove them from this manifold. So that is, Thurston's conjecture just uses these 2 decompositions. Okay, so this was an amazing achievement, at least for me, when I was reading his papers. And there are many key results of Perelman that were important for these results to happen. And one of the most important result was the monotonicity of Ricci flow in any dimension on compact manifolds. Now, why is the monotonicity of Ricci flow important? Monotonicity of Ricci flow means that there are no periodic solutions in geometry. So for example, if I want let's say I come back to this 2-dimensional case where I have some arbitrary metric, okay, I want this Ricci flow to take me to this nice constant curvature metric. Now, if my Ricci flow has periodic solutions in geometry, then I may go from here to here and then get back there. Okay? I might never go to this nice constant curvature metric. So I should first, because this is a nonlinear partial differential equation, I need to first rule out these kinds of periodic solutions. And Perelman did that. And another thing which he did is he achieved a complete understanding of all types of singular behavior on compact manifolds. So for example, that neck pinch that I showed you in the previous slide, what is the exact geometry of the neck pinch? What is the exact geometry of the thin region? Things like that. And then, of course, there's this technical point of how to implement Ricci flow with surgery, which is you do the surgery and then set an initial condition on the surgered pieces. So in the process, many radical new ideas and techniques were introduced to this field. Okay. Now, it's very surprising that almost independently and even before it was introduced in math, this Ricci flow arose in physics in a very natural way. Okay. So the key results of Perelman are important for physics as well because of this connection. And Ricci flow arises as a very natural kind of flow called a renormalization group flow in physics. So I know this is a maths audience, but because I'm a mathematical physicist, I do want to talk a little bit about the physics. And I want to give you a very rough idea of what a renormalization group flow is and how this Ricci flow arises in physics. So I'll take a very simple example, okay? So I'm going to take a system which is like a one-dimensional lattice, okay? And I've identified the last point with the first point, so it's like a ring. Okay? And I have these variables called spins on the lattice, which either take values -1 or +1. Okay? And I'm going to build up my physical system starting from these basic ingredients. Now this kind of a system in which I have a lattice and I have these variables taking values -1 and +1, it looks very simple, but it's the basis for explaining lots of physical properties. Okay? For example, if you want to talk about magnetism, this is the kind of model, not a one-dimensional model, but this is similar to a kind of model you will construct to explain magnetism. Then in this physical system, I'm sorry, we also have an interaction between these variables SI, which I call spins. Okay, we have an interaction between these spins, but this interaction is only of one spin with its nearest neighbors. Okay, so on a lattice, the nearest neighbors are these two spins for this spin in the center. Okay. And what does an interaction do typically? Well, what an interaction does is if you change the value of one of these variables, okay, then the energy of the system may change, and the amount by which it changes depends on the values of the nearest neighbors as well. Okay. Now in this physical system, what you want to do is you want to actually start with a model for a physical system like this. For example, if you want to explain magnetism in a piece of iron, you start with a model like that, but finally you want to find some quantities which can be measured in an experiment. For example, the amount of magnetism in a piece of iron or something like that. You want to find experimentally measurable quantities, and in this system they are obtained from this object called a partition function. So I'm going to explain what this whole symbol means in steps. Okay. So H, start with this object H that you see in the exponential, in the argument of the exponential. H is some constant times the summation of the value of the spin SI times the value of the spin SI plus 1, summed over all lattice sites I, plus some other constant times summation over SI, plus some constant times the number of spins N. Now this K, H, and C are real constants. Actually, I've taken them to be positive here. I forgot to mention that. And they're called coupling constants because when you see here, K actually measures this coupling between this spin variable and the next spin variable. So it's like an interaction between spins. So this is a constant that measures the strength of the interaction. Okay, so the measurable quantities in the system are not obtained from H alone, they're obtained from this object called the partition function. This is like, so let me explain what this is. So first you exponentiate H, H depends on the values of the spins at the lattice sites. Then you sum over the two possibilities for each spin. So you're doing that for every spin, so this is a product over all I. And I just stuck in a factor half here because that's the convention. Okay. So this is my physical system. Now I'm going to describe something called a renormalization group transformation. What the transformation is I'm not going to do all the summations now. I'm going to do this tracing or this summation only over alternate spins in Z. So I have these lattice sites. I pick out all the alternate lattice sites and I first sum over them. Okay, I first do this tracing over them. I'm sorry? Yeah, there is, but since this is a math talk, I'm not going into the physics details. I just want to pick out some essential features. Okay, so once I sum over these alternate spins, I will get something, and the summation is not easy to do. In fact, in this model, I can do it exactly. Okay. But if I do that, what I get is a very surprising structure. I get that my partition function, or that Z, can now be written as a tracing over alternate sites on a lattice with twice the lattice spacing and half the number of spins, and I have this exponential of a new function h prime of all these spin variables. And you can ask, what is the structure of h prime? Well, h prime has exactly the same structure as my original h. The only difference is that these k's, h's, and c's, which I call the coupling constants, have now changed. Now in this one-dimensional lattice, this is exact. Okay, so there are no additional dots here. This is an exact result. But if I go to two-dimensional lattices, three-dimensional lattices, this is not exact. This is approximate. So I can approximately write my partition function after this tracing over some spins as my original, in the same form as my original partition function, with this h prime being of the same form as h, plus some dot, 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 okay, where these are some additional terms. So the only difference between h and h prime seems to be that the coupling constants have changed in their values. Okay? And of course, this new partition function is now defined on a lattice with half the spins and twice the lattice spacing. So in the second step of this transformation, I can rescale my lattice length so that the lattice after step 1 looks superficially like the lattice we started out with. And I can do this process iteratively many times. Okay? Each time I do this, to a good approximation, h goes after the first iteration to h prime goes to h double prime, and so on, and the coupling constants just keep changing after each iteration. There is no, to a good approximation, there is no other change to the physical system. So in this expression, I told you there are some additional terms. I can't really do this exactly for all systems, but these additional terms get smaller and smaller with each iteration. So in my original lattice, my lattice spacing, if it was 1 unit, it's now become bigger, 2 units, 3 units, and so on. So what we're doing is successively zooming out in our description of the system. Now because this is an approximation, there is no natural inverse for this procedure, so renormalization group is not such a nice term. There's no group structure. Okay, so in most physical systems, we go in this way to a simpler looking physical system after many iterations. Of course, there are many notable counterexamples, so this is just something that you normally expect. Okay. So after a physical system, the description of a physical system after many such renormalization group or RG transformations becomes a simpler physical system. And the expectation is that after this procedure of going from this complex physical system to the simpler physical system is somehow irreversible. Okay. I'll try to explain what I mean by that later. Now you can also do RG transformations for continuum physical systems. Your lattice will now be replaced by Rn or some other smooth manifold, and your variables Si will now be replaced by functions, or more generally vector fields, tensor fields, etc., which are all defined on that smooth manifold. That function h of Si is now replaced by a functional of those fields, okay? And your partition function, which we define in terms of this sum, is now replaced by an integral, okay, where you exponentiated minus of this s, okay? And this d phi is a measure on the space of those fields, those functions or vector fields or so on. This integral is not always defined, so there are some procedures that you need to do to make it well defined. Now I have an example of one of these S of phi's, which looks like this. My variables, my spin variables have been replaced by these functions phi, okay, and these terms give you interactions between those functions, and these constants m square and lambda to the power of 4 that you see here are like coupling constants which measure the strength of the interaction, exactly like in the spin system. Now in the spin system we saw that when we did a renormalization group transformation, there was a discrete increase in the lattice spacing increased in discrete steps. Okay. Now here in this continuum case, you can do a continuous change in the length scales. So your length scales go from x to some b times x, where b bigger than or equal to 1 is a real parameter. And we saw that in the lattice case, your coupling constants changed after each RG transformation. Approximately that was the only change in the system. Here your coupling constants flow with respect to a parameter which changes continuously. This is log, conventionally this is log of this change in the length scale. Okay. This parameter t is called the RG flow parameter. So in the continuum, we can actually also make these RG transformations continuous. That was what I said in the previous slide. So the RG flow parameter t actually represents by how much we are zooming out in our description of the physical system. Each time we zoom out, our coupling constants actually change. In fact, they flow with the zooming out t. Okay? So this has been experimentally seen, because if you do an experiment to this physical system in which your experiment is not sophisticated enough to probe very small scales, then at the scale at which you are probing it, you will measure some value of the coupling constant. Well, if your experiment gets even is able to probe even less scales, then your coupling constant value will actually change. So this change in the strength of an interaction has been experimentally seen. So since these coupling constants change with respect to this, flow with respect to this parameter t, normally the flow is described by some differential equations which are either ODEs or PDEs. Okay? And these kind of differential equations are called renormalization group flows. Okay, so this is a very ubiquitous class of flows in physics. Now I want to tell you that Ricci flow actually arises in a physical system as a renormalization group flow. And the setting for this is a theory in physics called string theory, which has not been experimentally verified yet. But in this theory, the theory starts with a conjecture that the most fundamental unit of matter is a string of this type, a closed string or an open string. Okay. And in this theory, suppose I have some smooth manifold M with a Riemannian metric G. I have a string in this smooth manifold which the string moves, and as it moves it traces out a two-dimensional sheet called sigma. The sigma is an embedding, so is embedded in this M, and x's are the embedding coordinates. Then I can define a partition function for the system starting from this object S, which I actually had in my previous slides. It's just that S looks very complicated for the system. This S is defined on the sheet sigma, and I don't want you to look at the details, just note that Gij, G, which is the Riemannian metric of the underlying space in which this string is moving, now becomes like a coupling constant. I have to say coupling constant within quotes because it depends on the x's. It's like a coupling constant for this theory. It is technically a coupling constant if you expand this out in some kind of Riemann normal coordinates or something like that. You expand this metric out about a point. So I can think of this as a coupling constant. And Gij is just the ijth element of that matrix G, which I call the Riemannian metric. So when I do an RG transformation to the system, it flows, and the important thing for us is that the metric, this Gij flows, and its flow is precisely the Ricci flow. Okay? Up to these additional terms. So I have to tell you what this alpha prime here. Alpha prime also comes here. This is some constant. Okay? It is some natural constant in string theory. It's a very small number. So I can my flow to looks like Ricci flow to first order in alpha prime. There are other corrections which are higher powers of alpha prime, but alpha prime is very small, so normally people ignore these corrections. So I can think of this RG flow as just Ricci flow. Okay. So what are the questions of interest to physicists in this system? So in string theory, in a certain approximation, the solutions to this RG flow tell us how the propagating string, or which is just matter, changes the geometry of the underlying space. So I have this string propagating. As it propagates, it changes the geometry of the underlying space, and the solutions to this RG flow, the solutions to Ricci flow, will actually give you some insight into that. So the solutions to Ricci flow, singular behavior under Ricci flow are all of interest to physicists because of this connection. Now another important result from Ricci flow which is of interest to physicists is the monotonicity of the Ricci flow. Now the RG transformation in most physical systems suggests that somehow RG flow is irreversible, it leads you to a simpler physical system. So the fact that this Ricci flow is monotonic gives you an example of an RG flow in which this is true. So Perelman's result for Ricci flow confirms this, at least for compact manifolds. So I have about 5 to 10 minutes, so I'm just going to use that to introduce my last slides, which is to ask this question: can tools and techniques from physics give insight to questions in Ricci flow? And my claim is yes. And the most important area where this may happen is Ricci flow on non-compact manifolds. So a lot of the results of Perelman, Hamilton, and others were tailored to compact manifolds. Of course, it was because of wanting to prove the Thurston conjecture, but most of the techniques that were introduced in the process only work for compact manifolds. So Ricci flow on non-compact manifolds, well, not much work has been done in mathematics. And some of the results that I have obtained with my collaborators, I don't have the time to go into the details, so I'll just state them. Well, we proved that Ricci flow on asymptotically flat manifolds, which is a huge class of non-compact manifolds of interest to physics, we proved that this Ricci flow is monotonic, and we used a proof which is completely different from what Perelman did, because what he did is not applicable to non-compact manifolds. Then we also extended Perelman's results to other geometric flows which are related to Ricci flow, but on compact manifolds. And for the last few years, I've been interested in the stability problem of geometries under Ricci flow. This has a very nice connection to gravitation as well, which is one of my research interests. So a result which I proved was the linear stability of hyperbolic space in any dimension under Ricci flow. So this is non-compact hyperbolic space. Now these are all many of them are results on non-compact manifolds, and they were obtained by using techniques which physicists who work on gravitation and relativity are very familiar with. So this is new tools and techniques from physics which have been used to answer these questions. There are now many more tractable questions which can be answered by using this connection, and I'll leave that for some other time. Thank you. The mathematics, you mean in string theory, in the physics? Right. Oh yeah, I didn't define a Riemannian metric exactly. So I defined a distance function, and I said that the distance function comes from the Riemannian metric. So the distance function is a manifestation of the Riemannian. Okay. Yeah. The change in the curvature changes. Yeah, the curvature changes. So it's a flow of curvature actually.
So the curvature is varying along the pattern.
Yeah, so it is actually, Ricci flow is flow of metrics mod diffeomorphisms, so it's a flow of the curvature. Yeah. No, it may not be a fixed point. So for example, I have some arbitrary simply connected surface, right, that flows to the sphere metric. But the sphere metric is not a fixed point. The sphere also shrinks. It shrinks to a point under Ricci flow. But that doesn't matter because we already know that it admitted the sphere metric. So
that
Yeah.
It hasn't been experimentally verified.
Yeah.
A very naive question, how would you experimentally verify things to do with string theory?
Okay, so it's a very, first of all, it's a very complicated theory, and to experimentally verify it is very complicated because the size of a string is very small. So it is of some dimension which we cannot really measure by experiment. So if I say that the fundamental unit of nature is a string or matter is a string, then I have no way of splitting my matter to that small a size to see the stringy nature of it. So roughly speaking, all the experimental problems come from there. So it is, you might not be able to experimentally verify it in the near future, but it makes other predictions because it's something so drastic. It says that the fundamental unit of all matter is a string, so it makes predictions about behavior of matter, and then you can probably, well, you can't really experimentally verify that, but you can at least get some idea, get some idea about string theory and whether it's really reasonable or not. Yeah, by linear stability, I mean that you take the Ricci flow, okay, and then you consider linearized Ricci flow. Okay, so consider linearized Ricci flow, and then I would actually go to a related flow for which Hn is a fixed point, okay, such that from solutions to that flow, I can go back to solutions to Ricci flow. So for that linearized flow, I prove the stability result. Yeah. Yeah. No, so in the string theory picture, so your manifold M is a Riemannian manifold, but it is of a certain type. It's related to a space-time by just the analytic continuation. So you know that you can't always analytically continue all space-times.
So the information about analytic continuation is also a part of a matrix.
It's part of the RG transformation of a sigma model itself. You can't. So the result is only valid for those manifolds on which you can do it.